We'll start by doing a polynomial division question. So let's say that I asked you to start straight away with an example, e.g. x to the power of 4 plus x cubed plus 10x minus 3, and asked you to divide that by x minus 1. So there's a traditional way of doing this that you might have seen, which I don't much like. So where you'd write x minus 1 into x to the power of 4 plus x cubed, etc. And I don't want to do it that way. What I want to do is use a reverse grid method. So what this is actually asking is what times is by x minus 1 to make that. And that's the way I want to do it. So what times is by x minus 1 to give this expression here? Well, first of all, we want the answer to have an x to the power of 4 in it, because usually when we're timesing two things together, the answer goes in the grid here. So what has to go here is x cubed to make that x to the 4. But that's got a consequence now, because if we put x cubed there, this becomes take x cubed. So what we've got so far is x to the power of 4 take x cubed. But really we want our answer to have a plus x cubed in, not a take x cubed. So we're going to have to adjust for it. So here we need to add an extra 2x cubeds to make this work. So to make this add up to x cubed, that's what we've got to do. But now that we'll put 2x cubed there, we can say what goes here to make 2x cubed. So 2x squared goes there. X times 2x squared gives 2x cubed. But again, we can fill in the rest of the grid now, because that makes a minus 2x squared when we do 2x squared times minus 1. So minus 2x squared we've got. And notice in this one, we've got no x squareds at all. No x squareds at all. So to make no x squareds, we've got minus 2x squareds. If we add 2x squared like that, then we get our no x squareds, because there's no x squareds appear in this equation here. And that allows us to fill this bit in. X times 2x gives 2x squared. Filling this bit in here becomes minus 2x, because 2x times minus 1 is minus 2x. And here we've got 10x's plus 10x's, we can see, where we've got minus 2x's plus 10x. To get to plus 10x, we add 12x like that. So now we've got our 10x's. In order to do that, what has to go here has to be a plus 12. That's the only way. So x times plus 12, that's the only way we can get 12x. And filling this in, we've got minus 12. But minus 12 isn't minus 3. We need minus 3 at the end. So outside of this box now, the grid's full. Outside of this box, to get from minus 12 to minus 3, we add 9. And there we've done it. We've found what we need to times by x minus 1 to get to this expression here. We need to times by this. However, there was a remainder. So we'll go through a couple more examples like that. So in this case, the quotient is this here. X cubed plus 2x squared plus 2x plus 12. Then the bit we had to add on at the end, the remainder, is positive 9. Let's try and make sense of what each of those mean now, because we haven't quite finished this question yet. If I asked you to do, say, 7 divided by 2, what you'd give me back, we'd say, well, that's 3, and then there's one remainder. However, that remainder needs to be divided by 2. So in a normal sum like this is called the quotient, the whole number part, and the bit on top of the fraction is the remainder. So 7 divided by 2 is 3, remainder 1, but that 1 still needs to be divided by 2, but it's an important distinction to make. The remainder isn't 1/2, the remainder is 1, which because of the nature of the question needs to be divided by 2. So the quotient's 3 and the remainder is 1. So therefore the answer to this question isn't quotient equals this and remainder equals this. If I'm asked to do this here divided by that, the answer is the quotient, the whole number part, x cubed plus 2x squared plus 2x plus 12, and then there's a remainder of 9, but that 9 has to be divided by what we were dividing by, which in this case is x minus 1. And if you persevere with this, it becomes far easier and far quicker to do than the traditional polynomial division method. So let's do another one. In fact, we'll do a couple. So we've got these couple of questions here that I'll put on there, and see if you can do it alongside me. Try and stay a step ahead of me. So I'll do them very slowly to give you time to keep up. So find the quotient and remainder obtained in dividing that by that, say. So let's set up our grid. So we've got x plus 2 down there in our grid. And what the question's asking us is, what do we need to times by x plus 2 to get that? So that's what we're doing. X plus 2 times something else gives that. So our answer needs to have an x to the 4 in it. That's that term there. So write down on your grid what needs to go there to make the x to the 4. Which is x cubed. And that allows us to fill in this bit of the grid here, because 2 times x cubed is positive 2x cubed. So now we've got 2x cubed. Let's check in our answer how many x cubes we need. Where we can see here that there's no x cubes. We want no x cubes. So make an adjustment here to make sure that our answer has no x cubes in. So write something here to make no x cubes. So we take 2x cubed. Now let's write something here that makes this grid, multiplication grid, work again. We need to get something, write something there that gives us this bit here. So minus 2x squared does it. X times minus 2x squared is minus 2x cubed. But now we can fill in this number here. Now we can multiply out the grid. Find that number there. Minus 4x squared. Now we need 3x squareds. Positive 3x squareds. So we need to add something there to adjust this, because we've got minus 4x squareds currently. Put something else in the grid here to make sure that we get the plus 3x squareds that we need. So plus 7x squared will do it. So plus 7x goes there. To make the grid work, x times plus 7x is plus 7x squared. Fill in the missing bit. So that's the bit there. That makes plus 3x squared, by the way. So fill in the missing bit now. 7x times 2 is 14x. But we don't need 14x's. We need 9x's. So put something there so that we get the 9x's. So minus 5x. 14x minus 5x is positive 9x. Fill in the bit of the grid again. That makes the multiplication work. Minus 5. And then the last bit, minus 10. But check against the answer. We don't want minus 10. We want minus 12. So there's going to be a remainder here again. And the remainder is going to be minus 2, because minus 10 minus 2 gives us minus 12. So, minus 2 on the outside. Remainder equals minus 2. And the quotient equals x cubed minus 2x squared plus 7x minus 5. And in this one, it's important to answer the question exactly as it was asked. It didn't ask us to find the answer to doing x to the 4 plus 3x squared plus 9x minus 12 divided by x plus 2. It asks us to explicitly state the quotient and remainder, which is what we've done. So in this case, it wouldn't be appropriate to write the answer in that form, because that's not what the question asked. The original question here asked us to find the answer that we get by dividing that by that. And that's what I did there. Here, it's asked for the quotient and remainder. So quite often, questions might try to trip you up with that sort of wording. So let's do another one. Let's do this one here. So again, we've got that to divide by 2x minus 5. And it's asked us to state the quotient and remainder. So what do we have to times by 2x minus 5 to get that? So 2x to the 4 is our answer, goes there. So now let's fill the grid out. So put something there that makes this work. The thing you should put there is x cubed. Then fill out the grid. This column we can fill out now, because we get minus 5 x cubed. But we don't want minus 5x cubed. We want a total of minus 11x cubed. So put something in this space here to adjust for it. Which is that there. So now we can put something here to make this multiplication work. Minus 3x squared. 2x times minus 3x squared gives minus 6x cubed. And then we can fill in the grid. (15x squared). But we don't want 15x squared. We want 11x squared. Adjust for it. Make the total 11x squared. Minus 4x squared. So put something here that makes this multiplication work, which is minus 2x. And hopefully you're getting the hang of this now. Plus 10x. Minus 5 times minus 2x is plus 10x. We don't want 10x's. We want positive 18x's. Positive 4 makes that 8x appear. 2x times 4 is 8x. Finish the grid. Minus 20. But we don't want minus 20. So find the remainder based on that. We don't want minus 20, we want minus 3. So that tells us the remainder is positive 17. We add 17 to minus 20 to get to what we need here. And the quotient is x cubed minus 3x squared minus 2x plus 4. And we can make this even more difficult by giving higher order denominators. So I'm going to change my question again. I'm going to ask you to calculate x to the 4 minus 2x cubed minus 2x squared plus 7x minus 1 divided by x squared plus 2x plus 1. And I'll give you a moment to get started on that, and I'll maybe give you a few tips if you get stuck, or rather in case you get stuck. So have a go at doing that using exactly the same grid method. Make that look a little bit better. So the grid's just going to have more terms on it now, because what we're dividing by is x squared plus 2x plus 1. So I've just had a question. If we state the quotient and remainder as well as the answer, would we still get full marks if the question is asking to find the quotient and remainder? Yes, we would. Yes, we would. However, if the question asked us to calculate, like this one does, if you just gave the quotient and remainder as the answer, you would probably lose a mark if you answered with just the quotient and remainder for this particular one that's on screen now. So you probably would, but I suggest answering the question always just in the way that's asked. Right, we want this to say x to the power of 4. So for that to work, x squared has to be the case. X squared times 2x is 2x cubed and x squared there. So now we want minus 2x cubes, but we've only got 2x cubed, so we'll do a diagonal line like that, because the only other place x cubes could go is there. Put a number there to adjust for it to make us get minus 2x cubed that we need. Like that. What goes here is minus 4x, because x squared times minus 4x is minus 4x cubed. So multiplying down, minus 8x squared and minus 4x. So now we look to have minus 7x squareds highlighted in beige there, but we need minus 2x squareds. So we've got minus 7x squareds and we need minus 2x squareds. Well, if we add 5x squared, that gives us what we need. We've got the minus 2x squareds now. So let's put something here to make that 5x squared work. Positive 5. Let's finish the grid. Plus 10x plus 5. And let's look at what we need now. We need 7x's, but we've got 6 of them. We need 7x's, but we've got 6. That means there's an extra x. So the remainder has an x in it. And we've got plus 5, but we need minus 1. Take 6. The quotient is x squared minus 4x plus 5. Therefore, the answer is equal to the quotient, x squared minus 4x plus 5, plus the remainder divided by what we were asked to divide by, which was x squared plus 2x plus 1. There we go. So there it is there. Now this can apply to partial fractions. So let's move on from that now. So there's a worksheet for you to do. Worksheet B it is, that I've put online, that you can practice loads and loads of those particular types of example on. So go back, look at the recording. What I want to do now is some partial fractions. So we'll do a couple of notes. So partial fractions. And write this down. So when given a fraction with a compound denominator, i.e. multiple factors, it can be helpful to split it up into a sum of separate fractions. So let's just do a recap of adding fractions together. So let's say 2 over x plus 1 plus 3 over x plus 2. So the way I do this, I'd decide on what the denominator was going to be. So if I want to add those fractions together to combine them, the denominator is going to have an x plus 1 and an x plus 2 in it. If we multiply both fractions together, we can get the same denominator. Now the first one, to get it to say x plus 1, x plus 2, we multiplied by x plus 2. The second one, to get a factor of an extra factor of x plus 1 on the denominator, we're going to times both the top and the bottom by x plus 1 to get 2x plus 4 plus 3x plus 3 over that, x plus 1, x plus 2 equals, and that'll be 5x plus 7 over x plus 1, x plus 2. And there it is, we've added the fractions together. But what I'm saying with partial fractions, it can be helpful to take something like this and try and get it back to that form there. So I'm going to reverse this question now. E.g., write 5x plus 7 over x plus 1, x plus 2 as the sum of two separate fractions. So we know what the answer is going to be. We know the answer is going to be 2 over x plus 1 plus 3 over x plus 2. But it's how to get to the answer. That's the important thing. So step 1. Write an identity involving your initial expression and target expression. So the initial expression, 5x plus 7 over, try and do the fractions a bit better than that, over x plus 1, x plus 2. And we want to write it as the sum of two separate fractions. So the first is going to be a number over x plus 1 plus another number over x plus 2. So we want to write it in that form. So that's our identity. Step 2. Multiply both sides by the denominator of the left-hand side. And LHS is a commonly accepted abbreviation for left-hand side when it comes to mathematics. So multiply both sides by this denominator here. So I multiply the left-hand side by it. It just becomes 5x plus 7 is identical to, so a x plus 1, x plus 2 over x plus 1 plus b x plus 1, x plus 2 over x plus 2. And notice we've got a factor of x plus 1 and on both the top and the bottom, so those can disappear. X plus 1 over x plus 1 is 1, so we needn't write it. Likewise, they cancel as well. There's a factor of x plus 2 on both top and bottom, so we might as well not write it. So we can tidy this up a bit now. 5x plus 7 is identical to a x plus 2 plus b x plus 1. And truth be told, this step here we don't need to write really. It was just for illustrative purposes, for teaching. If you can do the cancellation in your head, feel free to. It's common practice not to put that line of working with the crossings out on. Right, so step 3. Choose tactical values of x to sub in find the values of A and B. So basically what we want to do to find what A and B are is recognise that this here is an identity. That means this works for any value of x. We can sub in any value of x we want and have this work. So there's some values to sub in that are easier than others. We can sub in any two values of x that we want to get two simultaneous equations in A and B. So if we wanted, we could sub in x equals 100 to get one set of simultaneous equations in A and B, and x equals 750 to get another set of simultaneous equations. We can solve those and find A and B, but there's actually easy values of x that you can sub in. For example, here, if I sub in x equals minus 2 into this, if I sub in x equals minus 2, then you'll notice that this bracket becomes 0 and the A disappears, allowing us to calculate what B is. So that's what I'm going to do now. Let x equal minus 2, because that's a sensible value to sub in. That makes one of the unknowns disappear, which means that 5 lots of minus 2 plus 7 equals no longer an identity because I've subbed in specific values. So the A x plus 2 disappears, leaving B minus 2 plus 1. So that'll simplify. So minus 10 plus 7 is minus 3. And minus 2 plus 1 is minus 1. So minus 3 equals minus B, which means that B equals 3. Let's do the same again. Let's sub in x equals minus 1 this time, which will make the B disappear. Let x equal minus 1, which means that 5 lots of minus 1 plus 7 equals A lots of minus 1 plus 2. And the B's disappear, which implies that, so minus 5 plus 7 is 2, and minus 1 plus 2 is 1, which gives us A equals 2. And we already knew that A was 2 and B was 3, because that's how we made the question up. A is 2, B is 3. But finally, conclude with the answer in the required format. So the answer to this is 2 over x plus 1 plus 3 over x plus 2. So I'll ask you to write another one in partial fractions. One thing you could be expected to do is factorize the denominator. So we do another one. I'll give you a moment to get it started off. But if you could write that in partial fractions, and as I say, the clue is the bottom, before we can do this, needs to be factorized. So give it a moment, start it off, and I'll finish it. The first thing to do to factorize this that. And our identity now, we want that to be identical to a over x minus 4 plus b over x minus 1. Multiplying both sides by the denominator of the left-hand side gives me x plus 2 is identical to a x minus 1, done the cancellation of the x minus 4s in my head, plus b x minus 4. And now sub in tactical values. That'll make that work. So subbing tactical values of x, that'll make the unknowns disappear, giving us values of a and b that work for that particular fraction. So I've got b is minus 1. X equals 4. So 6 is 3a. Meaning a equals 2. So conclude for our answer. A over x minus 4. And presentationally, you'd expect to write the answer like that. However, it just looks a lot nicer to do that instead. To have the take on the outside rather than on the numerator. Now I want to have a look at a special case here. Where there's a repeated factor on the denominator. So let's take, for example, this one here. That's about to appear. So there it is there. So when we've got repeated factors like that, there's a special thing that we have to do. A over x minus 3, all good, plus b over x minus 2, all good, plus c over x minus 2 squared. When there's a repeated factor on the bottom, x minus 2 squared, both the linear and the quadratic have to go there. So you have to put both the x minus 2 and the x minus 2 squared. So I'll just write that down. When a factor is repeated, we must use both the single and double factor. And you must remember to do that, otherwise you will get a wrong answer. Right, so now multiplying both sides by the denominator, we get 3x squared minus 7x minus 4 is identical to a, I think I'm going to run out of room here, I'll move that down a little bit, identical to a, and the x minus 3's cancel to give x minus 2 squared. One of the x minus 2's cancel to give x minus 3, x minus 2. And then both x minus 2's cancel to give plus c times x minus 3. Right, so now let's choose tactical values of x to sub in. So I'll let x equal 2 first. And I don't want to get caught out by arithmetic errors, so I'm going to start using a calculator here. 3 lots of 2 squared minus 7 lots of 2 minus 4 gives me minus 6 on the left hand side. And on the right hand side, now that x equals 2, anything with an x minus 2 bracket disappears to give c times, and 2 minus 3 is minus 1, which means that c equals 6. Let x equal 3. So I go back to the calculator, put that in, that one. Get the left hand side as 2. And anything now with an x minus 3 bracket disappears. 2 equals a times 3 minus 2 squared. 3 minus 2 is 1, square it, stays 1. So a equals 2. But we've ran out of tactical values of x now. So we're just going to have to use a different one. So as I suggest picking the easiest value you can think of, which for me is 0. Which means that in the left hand side, all the x terms disappear because they're 0. So minus 4 equals, and by this point we know a is 2. So a times, and if x is 0, it becomes minus 2 squared plus b. And we know x is 0, so that's minus 3 times minus 2. Then we know what c is from previous working. We know c is 6 times minus 3. Keep working down this line here. So we've got minus 4 equals, and let's put these two numbers in the calculator. Bit lazy, but better to be safe than make arithmetic errors. So 2 lots of minus 2 squared plus 6 lots of minus 3 minus 10. So minus 4 equals minus 10, and 3 times 2 is 6, so plus 6b. Taking the minus 10 over the other side, we get 6 equals 6b, which means that b equals 1, and we're done. So conclude. So we've got a over x minus 3, so 2 over x minus 3 plus b, which is 1 over x minus 2 plus c over x minus 2 squared. So the key point with this example, and the thing you've got to remember, when there's a double factor, like there, we must have the single and the double factor in our fraction. So there's another special case I want to go through. Where they can try and catch you out. Special case. Where the order of the polynomial on the numerator is greater than or equal to the order of the polynomial on the denominator. And again, this is one to watch out for. So I'm going to take now an exam question as an example. So you should always perform this check before you do a question. This is from an Edexcel exam paper on the old spec from 2013. And we can see here that the polynomial on the top is quadratic and the polynomial on the bottom is quadratic. So when this happens, we must do polynomial division before attempting partial fractions. So it's going to help to multiply out the denominator here to be able to do the polynomial division. So we've got 9x squared plus 20x minus 10 divided by x squared, 3x squared on the bottom, minus x plus 3x minus x plus 6x rather, minus 2. So equals 9x squared plus 20x minus 10 over 3x squared plus 5x minus 2. So we're going to do that polynomial division now. Otherwise, partial fractions just won't work. And that's again because the power of what's on the top, the order of the polynomial on the top, which is quadratic, is greater than or equal to, in this case equal to, what's on the bottom. So if we can do a polynomial division, we should. 3x squared plus 5x, take 2. And we want the answer to be 9x squared. So put a 3 there, that makes the 9x squared work. And finish it off. 15x, 3 times 5x is 15x, minus 6. And we're done. We've just got the remainder to find. So we've got 15x minus 6, but actually we need 20x minus 10. So the remainder, we need an extra 5x's, and we need to take 4. And the quotient in this case is just 3. So now that becomes our quotient plus the remainder over what we were dividing by, which in this case was x plus 2, 3x minus 1. If we put it back to its factorized form, and now we've got partial fractions to do. And this looks like the easy format that we did before. if we didn't do the partial, if we did the partial fractions first and we didn't do the polynomial division, we'd never have got this 3. So when the power on the top is greater than or equal to the power on the bottom, we must do polynomial division to simplify the expression before we do the partial fractions. So now let's move on to the partial fractions. 5x minus 4 over x plus 2, 3x minus 1. Let that be identical to a over x plus 2 plus b over 3x minus 1. Multiply both sides by the denominator to get 5x minus 4 identical to a. Do the cancelling in my head. The x minus 2's the x plus 2's cancel. Plus b x plus 2. And let's choose tactical values now to go in there. So I'm going to let x equal minus 2. Now I'll let you do this bit. I'll give you a moment for you to do this bit yourself, and I'll finish it off in a second. So a equals 2. Let x equal a third, which will make the a bracket disappear. Therefore, we've got it. But remember, there's a 3 plus at the start as well from having done the polynomial division. Again, if you don't do the polynomial division, you won't get that 3 plus. 3 plus a over x plus 2 minus 1 over 3x minus 1. And that there is basically partial fractions with all the exceptions that they can throw at you. So have a look, do the worksheets. Remember the special cases. But this is something really to practice, because in an exam, whilst the mathematics of it is straightforward, doing it accurately and in good time is the key. So practice lots and lots of these on the worksheets that I've put in the lesson area. And that's everything for today. So what I'll do next week, I'll be going through, it'll be rational functions, and possibly a little bit of binomial expansion as well. So see you back then.